I can't hear you.
Hit the wrong hotkey. Okay, thanks everybody. Uh, let's get going. Okay, so we're talking about Milestone 4, and I haven't, the header files are released, but I haven't, as are the tests, but I haven't formally released the instructions. That'll come out tonight. But you basically know from last lecture what this milestone is about. So we talked about how can we attack this problem. It's computationally hard, meaning we're not going to get perfect solutions. We looked at a greedy algorithm last lecture that should give pretty reasonable results. And you can kind of bring some cleverness to that greedy algorithm by making it think a little more about the future. We talked again about that last lecture. So we're going to keep talking about ideas of how can we improve our milestone 4 solution today. Okay, let's see. Okay, so just to remind you, this is what we did last week. We said, well, we could solve this problem greedily. We're going to make one decision at a time to keep things kind of simple. And the first decision we're going to make is we're going to start from some depot where our truck is, go to a pickup location, and we're going to pick whichever one of those has the shortest travel time. Okay, so for the problem I've got here, I've got 3 depots. Here, here, and here. So I got 3 different places I could pick the truck up from. So I said I'm going to look for, well, what's the shortest travel time I could have for the first thing I want to do? Getting from a depot to the first pickup location. Okay, so from this depot, there are 4 options. I could go to any one of these 4 pickup locations. So I could go and call find path to evaluate what's the time to get up to all of those. Then I have to do the same thing for the next depot, see maybe it's a better option, so 4 more. And then there's another depot over here, so 4 more again. So, for this relatively small problem, just to figure out the very first thing I want to do, which is what depot do I start at, what delivery do I pick up first, I need to do 12 calls to my find path routine if I want to get the travel time of each and pick the minimum one. Okay, so say I do that, I find my minimum travel time is this one. I should go from this depot to this pickup. Okay, so, and I already have the path, so done that part. Now I would go on and keep making decisions. Okay, but the problem is, this is slow, okay? So just calling this from every depot to every pickup, in this case, I don't have too many deliveries, but the larger problems we're going to give you in this milestone is, have D deliveries and M depots, and D could be about 100, and the depots could be about 10. If I multiply out then just for this first choice that my algorithm is going to make, I could call find path 1,000 times, and if my find path takes about 0.1 seconds for each call, it's 100 seconds. So already, and we're only going to give you 50 seconds. Okay, you got a 50-second budget to give us a solution. So this is already too long, and you've only tried to work out what are you going to do for the very first decision. So too slow, okay? And I see some good ideas in the chat, so that's where we're going here. So we talked last week about what can we do? Well, we don't have to call find path all the time. We can estimate the travel time between 2 intersections using geometric distance. And many of you are already doing that in Milestone 3 as part of trying to make an A-star algorithm. So we can do the same idea that travel time tends to correlate with geometric distance between 2 points. That's easy to compute. We could use this to estimate travel time, to choose a delivery order, and then call find path at the end when we've worked out our delivery order, just to hook everything together. Okay, and that'll be reasonable. We saw last week that would be fast enough, but we're going to lose some optimization quality because it's not perfectly accurate. Okay, so an example is here. I've got maybe here's a certain intersection that I need to make a pickup or drop off at. Here's another one. So I'm interested in the travel time between them. Geometrically, they're very close. So if I use a geometric estimate, I'm going to say the travel time is very small between these 2 things. But in fact, we've got a freeway in between. We can't go directly across like that. So we got to go around, and the real travel time is quite a bit higher. So this could make us make a poor decision about delivery order. It's not the end of the world, but could cost us some quality. Okay. I see Trevor asking, what if the driver gets out and walks? You don't want to walk across all, whatever it is, 12 lanes of the 401 either. So, Okay, so ideas, and I already see some in the chat. So I see people saying maybe we can make a one-to-many version or an M3 algorithm, or that actually has a name, multi-source Dijkstra or multi-destination Dijkstra. So that's exactly right. There are ways that we can do better than just using geometric distance. They take a little more code, but they are better. Okay, so we could pre-compute all the shortest paths that we might need, and then just look them up during optimization. Okay, so we could store these in a matrix or something kind of like a matrix. We have some from intersections, some to intersections. So if we have k interesting intersections, so there's a pickup, these are intersections that are part of a pickup or a drop off, um, maybe a depot, but they're interesting intersections, then we could basically say, well, let's find the travel time from interesting point one to interesting point K down here. So that would be the travel time to go from maybe the first pickup to the last drop off. And this might be the travel time to go from the last drop off to the first pickup, and so on. Okay, so every entry in this matrix gives us the travel time between two of the intersections that we're interested in. So if we had this, we could just really rapidly look things up as we're trying to decide whether a certain delivery order is good or not. But the question is, how can we figure this out quickly? Okay, well, we can figure it out quickly using geometric distance. That's fine. But can we do it more accurately using a path search algorithm? And the answer is you can do this. Okay, so you already have a find path algorithm that you wrote in Milestone 3. And that find path algorithm is an example of what's called the single source to single destination shortest path problem. So you start at one spot, some intersection, and you go to another spot, some other intersection. Find me the path in between those two things. Okay, so that's what you've written for Milestone 3 or are in the process of writing. So let's see. If we use this pre-compute technique, is this going to be fast enough? Could we just call our M3 function and it's fine? Well, we need the delays we might want to look up are from any delivery location, pickup or drop off, to any other delivery location, pickup or drop off. Okay, so if we have D deliveries, so let's say about 100 deliveries, our biggest problem I saw in the chat, people asking how big will these problems get? A little more than 100. I think in Toronto we have a test case that goes up to about 170. But to keep the math simple, let's just say it's 100. So I got about 100 deliveries to make. Well, each of those have, if there are 100 deliveries to make, that means there are twice as many pickups and drop-offs, 100 pickups, 100 drop-offs. And if I want to find all the paths between 200 source locations and 199 destination locations, well, I have to do this multiplication, and it's actually a lot of different entries in that matrix. I basically have a matrix with 200 rows and 199 columns, and the number of entries in that is almost 40,000. So it's actually a lot of travel times that I'm going to need to store. Okay, that's most of my travel times. It's the ones between the delivery locations. We also want to know what's the travel time from any depot to a delivery location. So if we had 10 depots or M depots, then the number of possible interesting travel times, if we have 100 deliveries to make, is a lot as well, about 2,000. And then at the end of our delivery route, we need to drop the truck off. So we want to know, well, we don't know what the end of our delivery route is yet. Could be any delivery location. So if we take all of those interesting delivery locations, 2 times D of them, multiplied by all the depots, is another 2,000 calls. Okay, so add all that up. For one of the relatively big problems we're going to give you, that's about almost 44,000 different source to destination travel times that you could find interesting. And that's almost 44,000 calls to your find path. If that find path algorithm takes about 0.1 seconds per call, which is reasonable, this is way too slow, right? It's over 4,000 seconds. And again, we give you a budget of 50 seconds. So you can't do this. So pre-computing seemed like a good idea, but this isn't going to work. Okay. But let's take a look at how Dijkstra's algorithm works. So let's say I'm starting at this intersection. That's one of the delivery locations, maybe a pickup or maybe a drop off. And these red points are other delivery locations. So places I know I need to go, I need to figure out orders to them. Okay, so if I run Dijkstra's algorithm, it's going to search out in kind of circles through the graph till it reaches one of these. Let's say that this was the destination that I said I was interested in finding travel times to. And then we're going to find it. We're going to invoke our backtrace routine. We're going to find the path, and we have one of our numbers. Okay, we know what the minimum travel time is from this location to this location. Okay, but what do we know at this point? These blue circles are basically, it's the limit of our knowledge. We've actually been computing more than just the minimum travel time to this intersection from this one. We figured that out, but we actually know a lot more than that at this point. So what do we know? I saw some people commenting on this early on, saying things like multi-destination Dijkstra. So you should know where I'm headed with this. Do we know more than just the minimum travel time to that this intersection? I changed my color here. At this point. And yeah, so I see people saying, yeah, we know a lot more. We actually know the minimum travel time to every single node in this circuit, every single intersection. And we're throwing it all away if we just end the search and we call our backtrace routine to figure out, yeah, that's the path that we used and what is the minimum travel time. And then we go and do another search. We restart our Dijkstra's algorithm to run a different search to go from there to there. Well, we throw away an awful lot of information because we actually know what is the minimum travel time to every node in those blue circles. Okay, so what should we do? Okay, so how can we leverage this? If we just end the algorithm now, which is what you do at M3, you found your one destination, so you're done. But if we end it now, we actually throw away all this work, and we're going to have to invoke this algorithm many times to go find the travel times to these other intersections. Yeah, so I see Wei Hang is saying, just keep going, right? Don't stop. And that's exactly right. So when you hit that destination, instead of stopping, just keep going until you've hit every single destination that's interesting, which is basically all of these interesting delivery locations, all your depots, all your pickups, all your drop-offs. Just keep going until you find them all. And then you can invoke your backtrace routine multiple times. Invoke it starting from there. Let me change this color again back to red. Invoke it starting from there, invoke it starting from there, invoke it starting from there. And you'll get a bunch of paths, right? You will get all of the paths. Well, you will, from this start location, you can get the path to every single destination of interest. Just keep running the wave expansion until you hit all the interesting intersections, and then invoke the backtrace routine multiple times. One from each interesting intersection. You'll get all the travel times to them and all these paths in one shot. Okay? Yeah, and Trevor's summary of that in the chat looks exactly right to me. Okay, so let's say we've now found a better way to do this. So we're going to do it's actually a relatively small code change, right? It's not a ton of code, but we're going to change our Dijkstra algorithm to be able to do what's called single source to all destinations. Okay, so we need the travel time from any delivery location to any other one. Okay, so that means we are going to start this for every single delivery location. Now, we can't do this in one path search. We're going to do, if we have 100 delivery locations, we're going to call this 200 times, right? We're going to start from every interesting intersection, which would be 200 in this case. Okay, we also need to include the depots. So we need to know what's the travel time from any depot to any delivery location. Same idea. We're just going to now start that multi-destination search from each depot. So let's say 10 more calls if we had 10 depots. And then at the very end of our courier delivery, we go from whatever delivery location we wound up to a depot. So we need to know from all of our interesting delivery locations, what is the travel time to each depot? How many calls do I have to make to get this? Okay, so if I had 100 delivery locations, I'm going to make 200 calls to kind of get from each of those 200 start points, what's the delay to every interesting endpoint. Same idea for depots. 10 depots, start a path search from each one of those to find the travel time to every interesting destination. Yeah, Sarah's exactly right. Sarah says we already know this. Okay, so we actually don't need any calls to get the information, the lowest travel time from any delivery location to any depot, because we can just consider the depots more interesting intersections, and we can get those travel times when we do these calls. Okay, so we're just doing one call for every start point, basically. So it's a lot fewer calls. Okay, so in total, if I had 100 pickups and drop-offs to make and 10 depots, this is 210 calls to this algorithm. You can do a little better. So I saw someone in the chat saying you could do a multiple source search. Okay, so you can get a little bit clever, and you can say, well, I can actually, for these depots, for this call, 10 calls, it turns out that I actually only need to know the shortest path from some depot to every delivery location, because that's all I need in order to choose what depot do I start at. So you can do another form of path search where you actually start not at one location, but you start the path search at many locations and expand out from all of them. And that's, again, a very small code change. If you do that, it reduces your number of path searches a little more, but it doesn't matter much. So if you want a challenge, you can just think about how can you make this extra trick work? You save a few path searches, but not many. It doesn't matter much. You can just do it this way and it'll work fine. Okay. So hopefully that was not too confusing. Any questions on how this works? Gerard, just type them in the chat or unmute yourself. I want to see if this is fast enough. Okay, so we've cut the number of path searches we need to do a lot by changing from a regular single source to single destination Dijkstra's algorithm to this single source to many destinations algorithm. So let's see if this is going to be fast enough or not, because we have this 50-second CPU time budget. So we want to pre-compute all the paths, because I'd like to get better path delay information. I don't want to resort to geometric because I want to get a bit higher quality. Okay, so we're going to have k interesting intersections. Again, I just showed you that if we have 100 deliveries, then k is about 200. Okay, about 100 pickups, 100 drop-offs. And we've got a graph with n nodes. N is pretty big. In most of our cities, it's 100,000 to 1 million nodes. What we're doing, this is the pseudocode of what we're doing, is we're basically just going through all these interesting intersections. So if there's 100 deliveries, this is about 200 interesting intersections. We're going to go from the first one to the last one. And for each one of those, each start point, source intersection, we're going to call this multi-destination Dijkstra algorithm, and we're going to call it with one of our interesting intersections. So delivery intersection of index. And then we're going to, as we do this, we're going to store the results in a matrix or something like a matrix, so we can look it up during our order optimization. So let's see if I can bring up a poll quickly on this. And okay, so I want you to work out what you think the complexity of this is, and I'll show it to you on the next slide. But so take a minute, and we've got these two variables. K, that's the number of interesting intersections, and N, that's the number of nodes in the graph. If we use this new multi-destination Dijkstra algorithm and we're trying to fill that whole matrix in of interesting delays, what's the complexity of all of that? And then we'll do some math to try to figure out, is this fast enough? Is this going to be feasible in our 50-second time budget? Okay, so let's give it a little bit more time. Let's see. Yeah, okay, so Trevor's asking a detailed question about super fast heaps. I'm just assuming a regular binary heap. Okay, so that's a typical implementation. Okay, so the kind of heap that we studied a few lectures ago. Okay, so let's see. Okay, so I'm going to give you a few more seconds. So if you're still thinking about it, take your shot, and then I'll end the polling. Okay, so I'm going to end the polling now. And so, yeah, the class believes that the most likely result, which I'm not sharing it, I don't think, is k n log n. Okay, with a reasonable number of votes for various other options. And yeah, k n log n is correct. Okay, um, these are kinds of questions we often ask, frankly, in the final presentation. So it's good to think about the complexity of some of the algorithms that we're coding. Okay, so let me stop sharing that. And let's go through why that is the case. But yeah, the majority of the class got that right. So that's great. Okay, so how do we work out the complexity of this? Sorry, let me just bring up my Zoom window again. Dijkstra's algorithm can search the whole graph. And when you have multiple destinations, so we're going from some start location to many different destinations around the graph before we stop doing the wavefront expansion, we're probably going to search pretty much the whole graph. Okay, so that means we've got n items to put in the wavefront. We're going to put and to pull out of the wavefront. So we're going to put every node in the wavefront eventually and take it out again. Okay, how much work is that? Well, if we're using a normal binary heap or priority queue, which is what we talked about in lecture, it's logarithmic complexity to add or remove one item from the wavefront. So that means for every start location, every one of our multi-destination searches, we're going to do an n log n computation. Now that loop that I showed you said we have to do this for every possible start location, all k of our interesting intersections. So we multiply that whole thing by k. So k n log n. All right, so that's complexity. It doesn't look too low, but it doesn't look too high. Let's turn it into time. We can execute a Dijkstra's algorithm on Toronto in around 1/10 of a second. So if k equals 200, because we have 100 deliveries, so that's one of our bigger problems. If I multiply this out, then we've got about 20 seconds. So it's going to be okay. That's less than our 50 seconds time budget. It's it's not hugely less. So I saw a question in the chat of, are these path searches going to take a significant chunk of the 50-second time budget? And the answer is yes. They, depending on exactly, we'll talk about some techniques in another couple of lectures about how you might be able to cut this down some, but it is going to be significant. If it takes too long, you can always fall back to using geometric distance to estimate. So you have some fallback options. Yeah, and Eric is basically saying multi-threaded. So that's something we'll talk about in a couple of lectures. That's one of the techniques you can use to speed this up. Okay, so those are a bunch of ideas of how we can get better estimates of travel time while we're optimizing and choosing delivery orders. Now let's go back to talking about heuristics for choosing delivery order, because so far we've talked about just one class, which is greedy. Let's just make every decision based on what seems like the best next thing to do. Another heuristic is multi-start. So you've got 50 seconds to get as good a quality as you can. Greedy algorithms are actually very fast. So aside from the path searches that we talked about, your greedy algorithm is going to take very little time. So you're going to wind up with time to spare. So you'd like to turn some of that time you have left into improved quality. So how can we do that? Well, yeah, I want to spend more CPU time, but I don't necessarily want to write more code. So what I can do is I can take the best of many results. I can just try different things, keep track of which one's the best, and just return that as my answer. And that's a classic technique that is called by multiple names, but a common one is multi-start. I'm going to try the same basic algorithm over time, multiple times, just starting it in slightly different ways so it gets different answers. And I'm going to take the best of those answers. Okay, so with our greedy algorithm, it's very fast. Um, we could run it multiple times, take the best one. But if I don't change anything, it's always just going to get the same answer. If I run the exact same algorithm over and over again with no changes to anything, it'll just return the exact same answer over and over again. So that's kind of useless. Yeah, so how can I make it get a different answer? And I see Isidore says, well, add some randomness to decisions. So that's a good idea. Okay. Um, so there are a bunch of ways we could do this. And probably the best one is what Isidore just said, add some randomness into its decisions, because that means if we have a lot of time left, we can just start it, make it do slightly different things, or run it again, and every time it does something slightly different. So we can just keep running it, getting, and have some probability of getting a different answer, no matter how many times we run it. So randomness is probably the best answer. It's not the only one though, right? So we can do this also by just running through a sequence of here are different things that are a little bit different. So we could force it to start at a different depot. The first greedy algorithm we wrote always started at whatever depot gave us the shortest distance to the first pickup, to some pickup. Well, we don't have to do that. We could say we'll run it again, but we'll just force it to start at a different depot. We could, instead of starting with the smallest travel time from any depot to a pickup, we could start with the second smallest travel time. And that'll make the algorithm do something different at the start and probably something different at every single decision. And this is where we get into randomness. We could have most of the time, the algorithm we coded last week always took whatever was the smallest travel time, to the next thing it could do, to the next delivery. We could say that 90% of the time it takes the smallest travel time, but there's a 10% chance of it taking the second smallest travel time. And the way you can code that is in C++, there are libraries for random numbers. So you can basically go ask for a random number between 1 and 10. And if it's not equal to 10, you take the smallest delivery. And if it's equal to 10, you take the second smallest delivery. So it's pretty easy to introduce randomness in your program by calling a random number generator. And you go to creference.com and it'll tell you all about those. Okay, so any of those work. And there's lots more ideas. There's lots of ways to make an algorithm do just something different. Okay. Yeah, and actually some people are pointing out that some people are throwing out terms like multi-armed bandit and so on. So yeah, this actually goes into a whole class of algorithms called reinforcement learning algorithms, which sounds fancy, and some of them are, but most of them are not that hard to code. All right, so trying things so we can just try different starting points, but you can go a long way with all of these algorithm ideas. There's a whole literature called reinforcement learning that tries to work out how can we make our algorithm learn what are good things to do. Maybe we shouldn't take a 10% chance of the second smallest delivery. Maybe we can actually have it learn what works better. That's kind of beyond what we're teaching in this course, but those are techniques that you can investigate if they interest you. Okay, so let's look at what this looks like. So the heuristic we coded last week, the second heuristic was called heuristic 1++. So it was our smarter greedy algorithm. And what it did is it looked through all the depots and it found what's the shortest travel time to some pickup. And it said, okay, let's do that first. Okay, so I do that. Then it looks at, well, what can I do next? What's the shortest travel time to the next legal thing I could do? So maybe it's a drop off, maybe it's a pickup. In this case, it's drop off what I just picked up. Then what's the next thing I can do that's close? In this case, there's only one legal thing you can do now, which is go pick up the last pickup over here. And then we're gonna have to drop that off, and then we'll go to the nearest depot. So we get this travel path, which looks a bit long, but every decision we made was actually, the greedy one. It looked like the best idea, but in the end, the travel path doesn't look fantastic. Okay, so we can just change something and run this again, because that algorithm's gonna be fast. So that previous time we started at this depot, we could just force the algorithm to start on a different depot. So maybe I'm going to pick the depot that gives me the second lowest travel time to some pickup. And that's up here. So I'm going to start there. I go to my pickup, then I go to whatever the closest legal thing I can do is, which is pick up A, and then I'm going to drop off A, and then I'm going to drop off B, and then I'm going to go to a depot. There's actually a lot less backtracking here, so you can see this is a better solution. Okay, started off with a longer travel time to, do the first thing, get the first pickup, but wound up with a better end solution. And this is a general technique that basically you can layer on top of any algorithm. If you have CPU time, you can just add some randomness or some variation into your algorithm and just run it many times. Doesn't have to be a greedy algorithm, it can be anything. It's most powerful if the algorithm you're running is very fast, because then you could run it a lot of times. Okay, so any questions on that? Kind of multi-start, trying to run things multiple times. Let's see. Okay, so Daniel's asking, are you going to be testing on random inputs or antagonistic inputs targeting certain solutions? Mostly randomly generated inputs. So we don't try to produce really weird test cases. The header files always talk about certain corner cases. If we in a header file document what you should do in some corner case, then we are going to test that corner case, okay, to see did you read the header file. Okay, you are not required to find the optimal path for milestone 4 because we don't know what it is, right? These are computationally hard problems, so we don't know how to get a perfect solution either. I'll talk about this tomorrow, but we'll basically give you certain anchor point solutions where we tell you for this quality, this is the grade you would get, okay? But you're not going to get optimal paths. We don't know what they are either. So, okay, so far we looked at greedy algorithms, we looked at multi-start. Another broad class of heuristics are called iterative improvement. So what these ones do is they say, well, it's hard to, in one step, construct a solution where you're pretty sure it's good. What you can do instead is take an existing solution, and maybe that was constructed using some smart heuristic. So I might have used a greedy algorithm to create that, but we got a solution that seems pretty good, but now we look at it and see, can we improve it? Okay, with small perturbations to it. So let's say I have some initial solution here. Okay, we connect everything together. And I don't want to draw these on top of a map anymore. It gets too hard to figure out. So I'm just going to remove the map and represent the solution just using edges in space. Okay, so this is still a depot. So this path starts in a depot. The numbers are travel times to get to the next interesting intersection. So this says I start at a depot and I take 2 units of travel time to make my first pickup, 4 units of travel time to drop that off. Then I make another pickup and so on. Okay. And if I follow through all these edges, I eventually at the end have made all my pickups and drop-offs, and I've wound up at a final depot. And if I add up all the travel times here, this solution has a travel time of 81. And it's legal because if I look through all of the pickups and drop-offs, I always pick things up before I drop them off. All right. So that's my solution. Maybe this came from a greedy algorithm. Maybe maybe it's just the order of deliveries that I was given. Doesn't matter. I now want to try to improve this using iterative improvement or local perturbation. Okay, so how would I do that? Well, I've got to change something. So let's say that I decide to change the order of this drop off and that drop off. Okay, so I'm just going to swap them. So if I do that, let's show that again. Okay, so if I do that, I just reconnect these edges in a different way. And I need to figure out what is the travel time of these new edges. And again, I could use multiple techniques for that. I could guess using geometric distance, or maybe I've pre-computed all the paths in the way we just talked about, so I can look them up and get a more accurate answer. I also have to check if it's legal. Okay, so and this one is legal because I'm still picking everything up before I drop it off. But there's some perturbations that might not be legal. Okay, so as I said, I need to compute new travel times. Maybe I looked them up in my matrix, so I've got that nice matrix built. And if I add all these new travel times up, it turns out that it's lower. Travel time is 72. It's better than my old 81. So I choose to make the change. If I found that it was worse, then I just wouldn't make the change. Okay. And so Sarah's asking, was this change from C to B random? Was changing the order of these two, like how did I choose that? And that's a good question. You can do it randomly. That tends to work pretty well, where you just say, let's just try changing something at random, see if it works better. If your algorithm's fast enough, you could just try a lot of perturbations. So you could just try swapping every single pair of intersections that you could. So there's many different techniques, but random works pretty well. If the algorithm's fast enough, you might just be able to try all swaps of two things because that's not that large a number. You also might, if your algorithm takes longer, you might try things that they seem promising. You go look for maybe long edges like this, and maybe you preferentially prefer to swap things that are connected to long edges like that. That also might be a reasonable thing to do. Okay, so that worked for me. I swapped the order of two intersections, and I got a gain, so I'm going to keep it. We can also try more powerful perturbations. So what I did there is I was just swapping the order of two deliveries. And that can be helpful, but it does change our solution in only a fairly limited way. Maybe there are bigger improvements possible if we make a more radical perturbation. And so a more radical perturbation that works well for traveling salesmen is called a two-opt. And what a two-opt is it means delete two connections in the path and then reconnect what's left in a different way. Okay, so that's a bit more powerful than swapping two intersections because it's essentially taking pieces of your travel route and reconnecting those pieces in a different order. So let's see how that works. So I want to delete two connections. So I'm going to delete this one and this one. Okay, so let's take them out. So those just faded away. This is no longer a legal travel route, so I need to reconnect things. There are actually multiple ways I can reconnect them. So I'm going to choose to reconnect this guy to here and this guy to here. Okay, so that's what I reconnected. This actually isn't legal for our traveling courier problem because we've got a depot. Well, we've got a path that goes like this, and then we're trying to go the wrong way on this edge. So when I reconnect this, I might have to like reverse the direction in which I traverse between two of my interesting intersections. I also have a depot that is not at the end of my path, so it doesn't make sense, right? My end of my path is going to be over here, so I should connect to a depot over there. Okay, so I need to do some fix-up in general. So I reverse what I just did there is I reverse the order that I'm going to go through this part of the route. And I remove the connection to this depot that was in the middle of my path, and instead I put a connection to a depot at the end again. Okay, and then I calculate my new travel time, and in this case, I'm making up these numbers, but it turns out it's better again. So I get a travel time of 70, it was better than 71, so I do it. Okay, so it's a little more work to do this, right? You have to remove two pieces of your travel path, two edges, reconnect what's left in a different order, and then you have some fix up. You can have depots in the middle. You can have pieces of your path that you're going through in the wrong order. You need to fix those. Okay. And I see a good question in the chat. Wouldn't some of the pickups be after the drop offs now? So for classic traveling salesmen, what I just showed you, we're done, right? We would basically have reconnected the path and we can just get the travel time. In this traveling courier, we can't drop things off until we pick them up. So we would also have another check. We'd have to write a check to say, is this legal? We just perturbed the path. Is it still a legal delivery order? If it's not a legal delivery order, then we have to reject it, right? It won't be accepted as a solution. So for traveling salesman, two-opt works very well. Okay, it's a very powerful perturbation heuristic. For traveling courier, it's not a bad heuristic, but it's a little harder to say. We may get less gain because of these legality constraints, because a lot of the two-ops, these path perturbations that we can make, will actually result in something that's illegal. So it may not work quite as well, but still worth thinking about. You can also think, well, maybe if 2-opt tends to produce things that are illegal, maybe I can think of something that is a little different than 2-opt, that for this problem is less likely to produce illegal solutions, but can still explore the space more than just swapping two deliveries. So you can come up with your own perturbation operator. For iterative improvement, the cleverness of your perturbation operator can matter a lot. So sometimes and for this problem, you can, with some cleverness, come up with some unique perturbation operators, and those can work really well. Okay, so any questions on that? So we kind of went through two different perturbation operators you could use: swap two intersections, or basically reorder entire parts of the path with 2-opt. Okay, so I'm going to show you like, well, what another way of looking at what the difference between these are. Okay, so let's say we're in this state. Okay, so I start at some depot. I go through a bunch of my intersections for pickups and drop-offs. I'm not marking which are pickup and drop-offs. And we get the following travel path. Okay, so we can see we've got kind of two edges that are long, right? That and that. Those are going to have pretty high travel times. So it seems like maybe we could do some local perturbation to improve this. So let's look first at the swapping the order of two deliveries. Okay, so let's say we decide that we're going to swap the order, not delete that yet. Let's say I want to swap the order of in number 2 and number 3. Okay, so if I swap that order, what that means is some of these edges disappear, right? Instead, my travel path would go from 1 to 3, back to 2, then over to 4. Okay, I compute the new travel time, and it's going to be worse, right? Clearly, this is not a good idea. Bouncing back and forth like that is just going to make my travel time worse. If you go through all the possible changes you could make, where you exchange the order of just two intersections, none of them will help you here. They will all make things worse. So we're stuck in what's called a local minimum. It's not a globally optimal solution. Okay, there is a better solution, but it's difficult to get to that better solution because small changes are making things worse. There's a big change that could make things better, but small changes just make it worse. Okay. All right, so let's compare that to 2-opt. So I said 2-opt is a more powerful perturbation operator. It can make bigger changes. So 2-opt, there are lots of different 2-opts here. Remember, it just means delete two edges and then reconnect the resulting path. Okay, so two edges I want to delete are those two. Those are my long ones. Maybe I try lots of random perturbations and eventually I, by luck, wind up doing that. Maybe my 2-opt looks for long edges and tries to delete them. Either way, let's say I eventually try deleting those two edges and reordering things. So basically what a 2-opt has done is it's cut my path into 3 pieces. Now I need to reconnect those 3 pieces. Okay, and there are multiple ways to reconnect them. So you could explore those different ways randomly, or you could try them all, whatever you like. If I try reconnecting them this way, okay, so 2 goes over here, 3 goes back over there. That actually doesn't work all that well. Okay, well, first I need to fix this up. This is the wrong order, so I need to reverse the order of those. Once I've done that, I can get the travel time, but it's actually not good. So this wasn't a good idea. Okay, but that's not the only way I could reconnect them. I could have reconnected them this way. Okay, so 2 goes to 7, 9 goes to 6. Still illegal. I need to reverse the order of this part of the path. Okay, so I do that. And I need to fix up my depots. I've got a depot off in the middle of nowhere. So I get rid of that and instead go to the closest end depot. And this is better. Okay, I've basically gotten rid of 2 long connections going, that used to go back and forth. There used to be one over here too. And now I only have this one long connection. So it is better, but it was a bit of a challenge to find. I needed a fairly powerful perturbation operator to find that change. Okay, so we can escape that local minimum. Let's see. Okay, so any questions on that? It's definitely a place where, like all of these classes of algorithms, you can actually bring significant cleverness to, right? You can come up with custom perturbation operators. You can make your greedy algorithm kind of predict the future a bit. So all of these are kind of classes of algorithms that you can play around with. Okay, so let's talk about how we represent the solution. Because we're talking about, I mean, I'm kind of drawing how we might change the delivery order, but your computer program can't draw this stuff. It needs to store it in some way. So one way we could store our solution is we'll just store a complete solution for everything we evaluate. So what you have to actually eventually return to the unit tests is a vector of what we call courier subpaths. And courier subpath is a structure, and it's got three things in it: a start intersection, an end intersection, and a sequence of street segments. Okay, so what does that mean? A subpath looks like this. We might say the start intersection is number 53, the end intersection is number 28 in my graph, and then there are a whole bunch of street segments with certain street segment IDs that get me from one to the other. Okay, so that would be essentially one of those edges that I've been drawing is one of these subpaths. And as I'm changing the solution, I could basically change all these subpaths in my solution. What do you think? Do you like that idea or not? I could do that. Should I do that? See if anyone is able to respond to this in the chat. So what do you think? This is like as I'm optimizing. So eventually I have to do this. I have to send the whole solution back to the unit test. But as I'm in my, say, an iterative exchange algorithm, like a perturbation algorithm, is this a good idea to store this complete solution representation? Yeah, so Wei Hang is saying it might be unnecessary. And it is. Okay, let me maybe just I'll show you what this looks like. Each of these little arrows that I'm showing is basically a courier subpath. Okay, so I could store the solution as a whole bunch of courier subpaths as I'm optimizing and perturbing the order of deliveries and drop-offs. But it's not the smartest idea. Okay. What I could do instead is I'd actually like to have a more succinct, easier to modify representation of my delivery orders, because you can attack this problem in basically two phases. Well, maybe three phases. You can say, I need to have a way to look up travel times rapidly between intersections. Okay, maybe that's geometric, maybe it's the matrix we talked about. Then I need to have some algorithm that, or maybe several algorithms that together come up with an order of deliveries. And then eventually need to fill in, well, okay, what are the actual travel paths between those intersections? The kind of most difficult part of that is choose the order of deliveries. That's the computationally hard part where there's no perfect solution. So I'd really like to make that part as powerful as I can. Let it perturb the solution, evaluate lots of solutions quickly. Okay, so to do that, it's better to have a more succinct representation of the delivery order and turn it into a full solution, a full route, only when you have to. Okay, so how would I do that? Well, I already showed you, this is my full solution. It's a whole bunch of courier subpaths. But I can, if I just want to represent the order, I could have a vector of, maybe I make a structure called pick or drop. So pick or drop is just going to say, are you a pickup or a drop off, and what's your index? So there's lots of ways you could store that, but basically I've made some data that tells me, what are you? Your delivery number 3 or your pickup number 4. I can have a vector of those. So I'm going to call that delivery order. And what does that look like? So it basically means instead of storing all of these street segments, all these arrows that I've shown in the top, I just store a vector that gives me the order of my pickups and drop-offs. So this says for example, for the path that I showed above, I actually pick up 0 first, drop off 0 next, pick up 1 next, pick up 3 next. That's what's in here. Pick up 0, drop off 0, pick up 1, drop off, pick up 3, drop off 3. That's here. So this is a much more succinct representation. Okay, it's a vector with a little bit of data in every single entry. That's a lot easier and faster for some iterative improvement algorithm to change. Okay, so sorry, a minute or two over, but I'm just going to try to finish off this section. What about the depots? Okay, so what I've shown here is basically I'm going to store the order of the deliveries, and that's what my optimization routines are going to work with. At the very end, I'll fill in the actual paths and return it to the unit tests. But I haven't put the depots in. Okay, so you got a couple options for depots. I could basically generalize this data class to say, well, you could be a pickup, a drop off, or a depot. And I can decide, maybe I'll have one variable that says, what are you? And another variable that's your index. That'll be fine. If I do that, I wind up with a slightly longer vector, right? So I wind up with depot identifiers at the start and end. And this, for example, says I start at depot 0 and I end at depot 2, which is exactly what my solution is. Okay, so with a couple more entries in my vector, I could store that. But I actually don't have to. You don't have to store the depots if you don't want to. The reason is the depots are not as important to the delivery order. Once you've chosen the order of your pickups and drop-offs, the right decision is always to just start at whatever depot is closest to your first delivery intersection that you've put in your order, and end at whatever depot is closest to the last delivery intersection in your order. Okay, so that means you don't actually have to store them in this representation. You could just figure out, you have to take into account what travel time are they going to add. Okay, so, but you don't have to store them in the solution representation if you don't want to. So it's kind of your call. Both ones are reasonable. Okay, and that is all I had to talk about today. So as I said, I should have the formal instructions for Milestone 4 up tonight. But based on these lectures and the fact that the header file's out there, you pretty much know what the problem is already. I'll stay on the line in case there are any questions, and have a good night.